Expected values. A random variable is a function that is defined on a sample space omega and whose range is a set of numbers. For example, if omega is the set of all graphs on n labeled vertices, we can define the random variable x by setting x of g to be the number of edges of g, or we can define the random variable y by setting y of g to be the number of connected components of g. Just as for functions, we can define the sum and the product of random variables over the same sample space the usual way, that is, x plus y of u is equals to x of u plus y of u, and x times y of u is equals to x of u times y of u. Possibly the most important and useful parameter of a random variable is its expected value, or in other words, expectation, or average value, or mean. Definition 15.16. Let x, which maps from omega to R, be a random variable so that the set S, which is equals to the set x of u, such that u is in omega, is finite. That is, x only takes a finite number of values. Then the number e of x, which is equals to the summations of I times the probability of x equals to I, summing for all I in S, is called the expected value or expectation of x on omega. Here and throughout this chapter, the probability of x equals to I is the probability of the event that x of u is equals to I. That is, the probability of x equals to I is equals to the absolute value of the set of u in omega such that x of u is equals to I divided by the absolute values of omega, the size of omega. In other words, E of x is the weighted average of all values x takes, with the weights being equal to the probability of x taking the corresponding value. Remarks. Some probability variables can be defined over many different sample spaces. Our above example, the number of edges of a graph, can be defined not just over the space of all graphs on n vertices, or all connected graphs on n vertices, but also on all graphs on at most 3n vertices, and so on. In each case, the set S, which is equals to the set x of u such that u is in omega, is different. Therefore, the expectation of x is also different. Therefore, if there is a danger of confusion, we write e omega of x to denote where the expectation is taken. If there's no danger of confusion, however, we will only write e of x to alleviate notation. Sometimes we announce both omega and x in the same sentence, as in let x of g be the number of edges of a randomly selected connected graph G on n vertices. This means that omega is the set of all connected graphs on n vertices, and x of g is the number of edges of the graph G in omega. It is possible to define the expectation of x in some cases when the set S equals to the set x of u such that u is in omega is not finite. If S is a countably infinite set, we can define e of x equals to the summations of I times the probability of x equals to I, summing for all I in S. As long as this infinite sum exists, see exercise 4 for an example. If S is not countable, then summation may be replaced by integration. Details can be found in any probability textbook. The definition 15.17. The random variables x and y are called independent if, for all s and t, the equality, the probability of x equals to s and y equals to t is equals to the probability of x equals to s times the probability of y equals to t holds.